Hello and welcome to the video review of the Electro-Automatique PS2042B power unit. Now, this is a device that hasn't been reviewed yet on the internet or on YouTube like most of the other reviews that I've been doing, and I purchased this device recently because my son wanted to join me with some experiments in the lab, and he wanted to test something he built with several drone motors, and these are rather serious motors and they're power electronics. And I actually found out that I had several power supply units in the lab, including this fancy Roden and Schwarz over here, but none of them actually was able to drive these drone motors in any reliable way. Why is that so? Because units like this Roden and Schwarz have a relatively modest overall power per channel. This is about 33 watts per channel. And that's certainly not enough for such a motor. Now, on paper, you can basically run the channels of these units in parallel so that you can run 3 times as much power, but I never got to run this in a reliable way, especially if you have like a changing type of load connected to the device. And down in the comments, I'll be posting URL of some discussions about not getting this type of parallel mode running reliable at all. So I was looking for another way actually to power up these electronics, and I decided to buy a power supply that can do a bit more of heavy lifting. And looking at the options on the market, I ended up buying this unit from Electro-Automatique. Now this is a pretty serious unit in terms of power it can deliver. It delivers up to 42 volts, it delivers all the way up to 20 amps. And altogether it can deliver up to some 320 watts of overall power. So that is 10 times as much as the individual channels here in my Roden and Schwarz here. And in this video review I'll be talking a little bit about its features and how it relates to other members of the family of PSUs that Electro-Automatique offers on the market. There's a whole series of similar type of power supplies with slightly different specs here. We'll be connecting the unit and we'll look a little bit at the user interface and also connect it to a load and see how it behaves. And then I'll be sharing my overall thoughts about this unit and provide you with my recommendations. But first we take a quick look at the device. It actually looks very simple. And I think that's kind of fine because this is a device that costs about 400 euros on the European market. So that's not particularly expensive, I think, for what's on offer here. And I can live with a unit that's not that particularly fancy looking. We do have a very solid device. We have a hard on-off button. I always like to see that. Here we got our 2 power terminals. Unfortunately, these are not at the regular type of spacing that you find in most power supplies. So those that have like this plug with 2 banana jacks in it, or for example those that want to do ripple measurement and they have this nice converter from 2 banana jacks to B and C, will be disappointed because you can't connect them right away over here. You'll have to construct something yourself. I would rather have seen that they would have used the regular distance between the power sockets here. For the rest, a very simple user interface, 2 buttons with the indent and with a push, and later on we'll see how that works. And actually they implemented it in a pretty nice way. We got 2 push buttons here and we got a USB connector, and that's rather in a strange location, I would say. Now you might argue if you connect this device by USB that you can't use the local controls anyway, so you don't need to turn any of these buttons, but nevertheless it's a bit of an odd position here, and I got the feeling that this was chosen solely on the basis of manufacturing considerations, that there's going to be like the control board here on the front, so the easiest thing was to have the USB connector somewhere here placed on the front of the instrument. It's a bit weird looking, but I can live with it. Otherwise there's not much to tell except that it's a pretty hefty unit, but then again we're talking about more than 300 watts of power it can deliver, and on the back side we got the power inlet and a small fan. Now if you turn the unit on, you very clearly hear the fan starting spinning. That takes about 1 or 2 seconds, and then it goes pretty silent again, and you hardly hear the fan even under rather serious loads of the device. So in that sense I think it's really well done. Now let's take a close look at the specification of the unit I'm reviewing here. So the one that I have here is like a no-frill power supply, supplies up to 42 volts and up to 20 amps. Got an overall total power maximum power of 320 watts, and has some basic remote control via USB, which I'm actually going to show a little bit more about in a second. This is part of a series of power supplies, and actually it's the second version of the second generation of this series. On top here you see the older model, and in particular a display was different, and it got a power button with a light in there, and the newer one, the one I'm looking at now, you see at the bottom. Now, as part of this family, you actually have a number of different models here, and I'm showing here a closer look. So you got models with a maximum voltage of 42 volts and models with a maximum voltage of 82 volts. And so those with 42 volts can be bought in several power configurations, but they go all the way up to 20 amps. That's actually the one that I'm looking at. And the one that go to 84 volts also on a number of different power versions with the maximum at 10 watts. So actually, for each of the different voltage models, you got 3 models available for 100, 160 and 320 watts of total power. Today I'm just looking at the single channel models, but I also like 2 or 2.5 channel models as well. You can find them on the website. Now, I already told you that I bought this power supply to complement existing power supplies in my lab that didn't go high enough when it came to overall power. Let's take a quick look how it compares to my Roden & Schwarz NG103 power supply. So in blue here you see the unit I'm testing right now, and obviously there's a power envelope that can go up to at up to 20 volts. It can deliver like the maximum power of 20 watts. Then there's a point in the curve where there's going to be like power limited, up to the point of 42 volts where it's going to be like voltage limited in terms of what it can do. Now, if we look at the Roden & Schwarz, a regular one channel is the orange line. That's really a completely different level of power. That's not to say it's a bad power supply. I like the Roden & Schwarz power supply a lot, but they're simply not meant to deliver this type of powers. And if you would try to put the Roden & Schwarz in parallel operation, you would go to the gray line or even the orange line. Even then the gap is big, and like I said, I never got this parallel mode operation working reliably for really fluctuating loads or practical situation. I mean, with a lot of effort I can get it working with an electronic load very carefully set, but otherwise not really. Now let's take a quick look at the inside of the Elektro-Automatik as well. Here you see some pictures. It's fairly straightforward what we will find in a switching power supply here. Overall, I have a pretty solid impression of how things are done. We see several cooling plates. We see a big one there, more on the left side, where we got the power sticker on, where's the hard power silicon, and we see some more all the way up at the end. And actually there we got more like the diodes that are connected to that one. And on the right we can see the PCB where the screen is on, and the vertical one that we see right over there at the front right, that is the controller unit. Take a little bit more detailed look. Here we see the silicon that switches the actual power supply. We don't get to see its type because it's heavily shielded here, connected to the metal plate behind it. There are also places, if you look at the construction resistors, it kind of looks kind of odd. It looks like you see a number of transistors actually on the top of each other. It seems that eventually they were using kind of bigger resistors than they were originally intended to do so. But I guess that's only a good thing. I think they realized in time that perhaps this particular version of the power supply, like the highest version in the series, apparently required some higher spec components, and they must have done so. Now this is the little vertical PCB where you see the controller unit residing. I looked it up. It's an NXP micro controller. It's an ARM M3 processor. Must be fast enough for this purpose. And here, and take a moment to take a good look what you're seeing here. You see the power terminals, the output power terminals, but seen from the inside. So red on the top and black, that's a bit of harder to see at the bottom. We see these thick wires come here, and we see the measurement wires. But the interesting thing, and that's why I'm showing you this picture here, there are two capacitors right over the output terminals. There's a smaller one, more like high frequency suppression, but there's also a bigger one. Can't see its value from here right now. Might be 100 microfarad or something. And later on, actually, when we do a measurement, I reflect back on the fact that we find this capacitor here right away in this point of the unit. Alright, let's start to take a look now at the device itself, do a little bit of testing on it, and I set up a little test space, and we got the power supply here, we got the DMM which is connected to the output of the power supply, and we got an electronic load down here. So first what we'll do, we'll turn it up and we see how long it takes to power up. So there we go, 1, 2, 3, 4, 5, 6, 7, 8, 9. So approximately 9 seconds it started up. You might have heard there was a little bit of whining of the fan coming in, but then it disappears again, and actually the device stays very quiet over almost all its operation, even when loaded pretty hard. So now we see the display turning on. We see in blue the voltage, in red the current, and we see the actual voltage and currents. We also see the set voltage and current over there. And it's like a very clear, clean display. Now to set any voltage, basically work from the voltage knob over here, and you might see here this little line, and that line is basically the digit that I'm editing. So if I go up and down here, I will be turning on the voltage. If I press it one time, I would go like full digit. So actually it's a fairly convenient interface, and the setting of the power will be exactly like that. So let's go here, and so let's put the power at 19 amps. Otherwise, in terms of setting of device, is pretty basic, simple and basic. We got a settings buttons over here. We get a little menu with settings, overview, and a couple of setup issues. So if we go to settings, use the push button, and we get all the settings, and we can change here as well the settings that we're interested here. And actually we also get here the protection and the limit values that we can do here. If we go back to overview, we actually get to see exactly the same things, but we can't change them here. So that's a little bit redundant, I would say, the overview. There is the human interface menu with some language setting, and you can lock the device and have a PIN code enabled, etc. And finally there's some information about the hardware and software version. There is a utility that you could update the firmware, but I didn't find any firmware at all for this series on the website of the manufacturer, so I haven't tried anything like that. Okay, now let's go and start and use the unit a little bit and see how it behaves. So turning it on and off goes via the little button over here. Actually, if you've got a lot of cables, it is a little bit cluttered, especially if you've got like the USB cable that we'll be using for a little experiment in a moment. So I'm turning the device up. It says it goes to 10 volts, and on the DMM I see that actually that measurement is fairly accurate here. Now if we add a load to it, so I set here the load down here, the electronic load, at 60 amps. So that's pretty serious. So if we do that, we got 170 watts already being supplied by the device. We see the power supply still says 10 volts. The actual voltage, as I measure it here from the terminals, went down to 9.8. So that probably has to do with that the voltage measurement inside is not right away on the exit terminals, or for some other reasons he might be a little bit optimistic what he's measuring. but it's not a great deal of voltage that I would be concerned about in any way. Now the next thing that I would like to explore a little bit is the computer interface that it's supplied by the manufacturer. And if we go here to the computer, we get to see the so-called EA power control. And first of all, we have to go and look for our device, and there we got see it popping up right here on the screen. And we got a couple of things. We got what is called the terminal, we got a settings menu, firmware update, sequence log, and a couple of calibration and other things that are not activated now. I think you can activate them by additional software licenses, which I don't have. Now, the most interesting of these is the terminal application. So I'll start it here and start it for my device. So this is how the terminal looks like, and we recognize here again the screens that we got on the device itself as well. 10 volts, 18 amps right now. And nicely we also see the power here in green. This is actually how it looks on a couple of other devices by Electro 8 Automatique as well. Actually, I think it would have been actually nice if the power would also be shown on the unit itself. There is enough screen real estate for that, and like this in green, it's very clear. Anyway, you only get to see it in this user interface. You can control everything from the device, and then you would see the setting change. You can also control it from the computer right now. So I'm going to remote on, and so we get to see here that I could change the voltage, and the device would of course follow nicely. And I can also take the unit like on and off, and we would see it doing exactly like that. We see also the overpower connection, like the overprotection voltage, the over current voltage, and the overpower voltage. And we also got some command scripting languages right here. So here, for example, we can send out a message, reach device type, and we would get to see some data on it. I think if we go here, this is another scripting language, it's going to be a little bit clearer. Yeah, if we do identity question mark, then we get to see the electronic arts. If we do measure power, then we're going to see the 184 watts or so. There we go, that the device is currently supplying. And the set voltage here, we would see 320 watt. That's the one we that's actually set a little bit higher, the protection, but that's the overall deliverable power. So this is a fairly usable interface here, I would say. Let's turn the remote control off again. Close the program. There's one more part that I would like to show you here, and that is the sequence log. And that's a pretty powerful sequence manager here, where you can program in a number of steps, like a voltage pattern over time. I'm not going to go in detail now, but I think for such a basic power supply, this is actually a fairly nice functionality. I've been playing around a little bit with it, and it did what you would expect it to do. We also have a settings app here, but most of the settings here are not particularly relevant to this device because we don't have an Ethernet interface and some of the other interfaces that we might be interested here. So that one has limited power for the device that I'm testing right now. Alright, I would now like to look a little bit more how the power supply behaves under a load, and therefore I also connected up the oscilloscope here. And in yellow on channel 1 we see the voltage coming out of the device, and on channel 2 in green we see the power delivered by the device. Now, how I'm measuring the power, the electronic load that I'm using here actually also has specific outputs that represent the voltage and power over the electronic load to a BNC output, and I'm taking that by the oscilloscope. And so the green line that you're seeing basically has a approximately 5 amps per octave or per decade, I would say, view on this screen. So very simple. Let's just turn the power supply on and off, and let's see what we see in terms of the voltages and the power. So we turn it on now. Turn it off. And one more on and off. I'm going to stop it right here, and the load currently is at 18 amps, so that's a pretty hefty amount here. So what we actually see on the screen, that it seems to be pretty well behaved. There's definitely not any overshoot. If anything, it's slightly slow in the way that it's kind of reacting. We could take a little bit better look how slow or fast that is. So let me see if I can kind of get that bigger on the screen. Slightly smaller would do. I'm going to use the cursor of my oscilloscope. Oh, let me see, the cursor right now is on horizontal. We want to have a vertical cursor. There we go. So we're going to put cursor point 1 over here. We're going to put cursor point 2 where the final voltage is reached, well, 230 milliseconds, 0.2 seconds. So it's kind of slow in responding, but I think that is perfectly fine for a heavy power supply of the type that we have here. And also in terms of going down, we see the same type of behavior. It takes like a few hundred milliseconds basically to get down again. You might be a little bit surprised. What you see here is that even if the volt is already down, he's still delivering all the power. That must be that the measurement coming out of the electronic load lags a little bit behind, because of course there's no reason to believe there can be significant power flowing if there's actually no voltage, no potential anymore. So that should be the delay that basically comes from the device over here. Now, I just did this experiment under having a little bit of power here. Let's do the experiment again when we don't have the load here. So we go again. Let's put the oscilloscope a little bit slower. So let's go to the voltage again. So we see no power. And we turn it off. Yeah, and this is what I wanted to show you. Basically, very, very, very slow. So it actually happens that it takes like perhaps as much as 10 seconds or so if you take off the if you turn off the power supply and there's no load to get back to 0 volt. Let's try it once more. We're turning it on, set at 10 volts, no load, and we turn it off. We also see it on the device itself. 5, 4, 3, 2, 1. Now I think that must be because of the capacitor we saw before that was actually right over the output terminals of the device. Fine too, but you just want to be aware that if there's no load, there is going to be some power over the terminal for quite a while there. Now we can also take a look a little bit more at the dynamic behavior of the unit, and that could be done by using some functionalities here that we got in the electronic load. So what we can do here is actually turn the electronic load on, off and on pretty fast here. I'm going to do that with 15 amps or so and see how the device behaves. So I'm going to turn that function on and I'm going to power my device. I actually might want to go a little bit faster here. Turn it off again. So we turn it on and now we see on the oscilloscope a little bit of voltage fluctuations. But I would say this is nothing really to worry about. If we think about that, we're actually now switching something like 15 amps on and off all the time here. We see really very small fluctuations here that I will be perfectly fine with. Now this has a certain rise time and fall time that can be seen on the scope of the or on the display of the electronic load right now. To look a little bit more how it behaves if we turn things on and off very fast, I also prepared a little program on the electronic load that's a sequence of different load situations. So let's try and go that. We're turning on the oscilloscope again. I'm going to try to find where my little program is. That is going to be under the program settings. Turning the device. So this is going to load the power supply first by 1 amp back to 0, by 2 back to 0, by 3 back to 0, and then a couple of more steps like that. So we should start to see things rolling. I'm turning off the power supply and I'm triggering this particular function, and yes, we see on the oscilloscope basically the steps coming here. We're now at 8 amps, 10 amps, 12 amps, 14 amps, 16 amps, 18 amps. I think that was the last in my little sequence here. So let's take a look at the screen of the oscilloscope. Yeah, we do see a little bit of voltage fluctuation, particularly when a large rotor is being turned off. But then again, they're fairly small here. I think we could probably zoom into that a little bit more. Like the largest step that we just have here on the oscilloscope. We see here a bit of noise. We see it going up and down, but these are really very small amounts of voltage. So I think it's a very predictable power supply. It's not fast, but it's precisely what I would probably want under heavy loads and predictable type of behavior. On the oscilloscope, if we now magnify the signal like this, we do see a little bit of noise. I wouldn't take these measurements as accurate, because actually I'm just using normal banana leads here, and any measurement of the noise of the power supply should really have a different setup, either by proper coaxial cables that would start right away over here. And here we have this problem again that the favorite type of connector that you would like to use there doesn't fit, because they're not at a regular distance. You would have to construct something yourself to connect a coaxial cable here that would have to go shielding right away to the plus and not pick up something. And that's a much more precise task, I think, to measure the noise of power supplies. Maybe you even want to engage a differential measurement probe, but then you also want a differential one with very little noise. That's not the purpose of the exercise I wanted to today, so I'm actually not going to do that. But altogether, I think I can say that this power supply really behaves exactly what I wanted it to behave, I think, for a device in this category and for this type of purposes. Very solid, not very fast, but I think that would actually be my preference for the purposes they have in mind for this power supply. Now, finally, the conclusion. I think it's pretty straightforward. I like this unit. It performs well to expectations. It got lots of power, especially if you consider the street price, which I think is rather fair. It's a simple but a well done user interface. I've been using it without even thinking of it. It's quality built. It has very silent operation. If any noise that you heard during my experiment here, it was probably the electronic load that had to get rid of this 200 watts or so of power it was dissipating, but not the unit itself. Small thing, but it's got a hard power button. I always like that. On the minus side, some people might think it has rather simple looks, which is the case. It got a bit of an odd position of the USB socket right away on the front. I would have liked to see that differently. And the output terminals are not at the standard distance, so it's kind of harder to connect like converters to, for example, BNC, if you want to engage in ripple measurements or for any other reason would like to do that. But I think overall this is a very nice unit.